All right, section 3-8 is on the derivative of sine and cosine, and as you may recall, the objective of this section was to derive the trig rules for the derivative of sine and cosine. All right, that leads us to what is called the general sinusoidal equation. And now that I know the derivative of sine and cosine, I can now come up with some real world phenomena that can be represented with a sinusoidal curve. That is a transformation of sine and cosine, and use it to answer some questions about that particular phenomena. All right, so let's take a look at our general sinusoid. Now you can write this in terms of sine or cosine. We're going to do this in terms of cosine, and I would suggest that you do that as well. But we have y is equal to c plus a times the cosine of b times x minus d. Okay, now the a, b, c, and d there all represent translations and dilations. That is, a translation is a shift of this function, or a dilation is a stretch of this function. And there's 4 of them because of the fact that some of those are vertical, some of those are horizontal. So you have vertical and horizontal dilations and translations taking place there. All right, so let's look at what each one of these represent here for us. So let's just go in order here, alphabetical order, I guess is what we're going to do. So the amplitude is actually the absolute value of A. Now the amplitude there is always positive, and that's why we take the absolute value of A, because A could be negative. So basically ignores the sign there of A to get the amplitude. And that value there, notice that you're multiplying A times the cosine function. That's a vertical stretch then, a vertical dilation is what I'll write here. It's a vertical dilation of that function. Okay, so the amplitude actually indicates the vertical dilation, but with a sinusoid we call it the amplitude. All right. If you take a look at what b represents, now actually the period is equal to 2 pi divided by the absolute value of b. And again, b could be positive or negative. So that's why we have to throw away the sign there, because the period is always positive. You could solve this for b. In fact, I'll just go ahead and write that next to it here. We could say, or the absolute value of b is equal to 2 pi divided by the period. You can write it either way. Okay. Now what the b actually represents, you notice you're multiplying the b times the x minus d there. And so since you're affecting the x value there, that's actually a dilation horizontally. And it's actually the reciprocal of the horizontal dilation. Okay, and because of the fact that we write it as just b, that's why it turns out to be the reciprocal. If we wrote that as 1 over b, then b would actually represent the horizontal dilation. But it's not written that way. That's just by tradition. That's how we write it, so we are not going to change it here. But it's actually the reciprocal of your horizontal dilation, how much you stretch this thing horizontally. All right, the next one is the value of c. And c is what we call the sinusoidal axis of this sinusoid. Another way to describe that is a vertical translation. You'll notice that you're adding that value of c to your cosine function, so it's actually the vertical shift up or down of this function. But we call it our sinusoidal axis. And the last piece there is what we call our phase displacement. And that's what d is. D represents the phase displacement. Or again, you can see that you're subtracting that from x, so it's actually affecting the x value. That's the horizontal translation. Okay. So in blue there, what I've written down, those are the, in terms of translations and dilations, what we're actually getting. But the terms that we use to describe this with a sinusoid is what we have written here: amplitude, period, sinusoidal axis, and phase displacement. All right, one last piece that we talk about with a sinusoid is the frequency. And the relationship between the frequency and the period is that they are reciprocals of each other. So the frequency is 1 over the period. Or literally, that would be the absolute value of b divided by 2 pi. If you just wanted to literally take the period that we wrote up above there and just reciprocate it, that's what you'd end up with. Okay, so if you're asked about frequency, usually what we do is find the period and then just reciprocate that, and you got yourself the frequency. Or vice versa, if they give you frequency, reciprocate that, that tells you the period. All right, let's draw a sketch of this to kind of fill in all the details here of what we're actually talking about and how each of these pieces fit into this particular graph here of a sinusoid. So let's sketch a sinusoid. I'm not going to worry about sketching something too accurate, but we'll sketch at least one period here of a sinusoid. And so let's start with the vertical part of this here, the vertical dilations and translations, if you will. So this line that goes right down the middle of this is called the sinusoidal axis. That's what that value of C is. C is the sinusoidal axis. Now here I've drawn it as C as a horizontal line. Doesn't have to be that way. C could be some function, like a linear function, so this actually would have a slope to it. Or it could be any other function for that matter, which means your sinusoid would oscillate back and forth around that sinusoidal axis, whatever that curve is. Most of the time we'll find it's going to be just a horizontal line or a straight line. Could have a slope to it. And then if you measure that distance from the sinusoidal axis to what we call here our upper bound, I guess we can continue this all the way over there. Or if I measure that same distance to the lower bound from the sinusoidal axis, that distance right there is the amplitude. So this distance right here is the absolute value of A. This distance right here is also the absolute value of A. So if you want to name these points here, this would be C plus the absolute value of A, and this would be C minus the absolute value of A. Okay, so that marks what's going on our vertical axis there, the amplitude and the sinusoidal axis. And then on the x-axis, on our horizontal axis, with the cosine function, what you need to find is where the maximum occurs. So I'm going to just pick one of these. It doesn't matter which one you pick here. I'm going to pick this one right here. And that maximum actually tells you the phase displacement. That's the d value. Okay. And then the last piece to this is to determine the period, which again, the period is the distance in this case from one maximum to the other next maximum, tells you the period. So this distance horizontal here is the period, which of course is equal to 2 pi divided by the absolute value of b. So I guess if you wanted to name this point here as d plus that 2 pi over the absolute value of b, you could. That usually isn't necessary to name it, but that would be the name of it. Okay, so there's the A, B, C, and D and how they all fit into our graph. So given the graph of a sinusoid, you should be able to come up with the values for A, B, C, and D, thus get your general sinusoidal equation, and then be able to do some calculus with that. So let's try that with an example here. Look at example 1 there on page 110. It says you have a mass that's bouncing up and down on a spring hanging from the ceiling. Its distance, y, in feet from the ceiling varies sinusoidally with time, t, in seconds, making a complete cycle every 1.6 seconds. And it says at t equals 0.4, y reaches its greatest value of 8 feet, and the smallest y gets is 2 feet. So they've given you a verbal description of this function. Remember we talked about different ways to represent functions. They've given us a verbal representation of that function. I want to take that and create a graphical representation of the function. So I can then take that graphical representation and come up with the algebraic representation or the equation of that function. Okay, so there's kind of a multi-step process that we're going to go through here. So let me first start out with a sketch of this thing. Now, for part A, it says to write an equation for y in terms of t. So that's the goal here. So that's why I'm going to start out with the sketch of this thing. I'm just going to mark, I'm not sure exactly what my axes look like here. It really doesn't matter. I'm just going to simply sketch a general sinusoid in here and just mark in the values that they've told us. So they said, starting with the first piece of information they gave us, it says it makes a complete cycle every 1.6 seconds. So in other words, the distance from this point to this point is 1.6 seconds. So this is 1.6 seconds. In other words, the period is equal to 1.6 seconds. The next thing, it says at t equals 0.4, y reaches its greatest value of 8 feet. So right here has got to be 0.4. At t equals 0.4, it says that you reach the greatest value of 8 feet. So that's 8 feet up here. And finally, it says the smallest y gets is 2 feet. So the lower bound for this function then is 2 feet. Okay, so with that, I've got basically all the pieces that I need to come up with the equation. Let's just add in a couple of other details here. First of all, the sinusoidal axis is the line that goes right down the middle of this. So that's the midpoint from 2 to 8 there. If I just find the midpoint value or average those two numbers, I can find the midpoint that I'm looking for. So 2 and 8 gives me 10. Half of that is 5. So 5 must be the sinusoidal axis. Not only that, but I'm going to need to know my amplitude. And so the amplitude, remember, is the distance from the sinusoidal axis to your upper bound or lower bound, whichever one you want to look at. So from 5 to 8, that's 3 units there. That's my amplitude for this function. The phase displacement I've already got marked. That's the 0.4. And the period I have is 1.6. And I can use that to come up with my value for b. All right, so that's the pieces that I need in order to come up with my equation. And they said that y is a function of t here is what we're working with. So I'm going to write it that way. I'm going to write it as y of t here, just to use a function notation when I write it. And the general equation, I guess I'll go ahead and write the general equation again, and then we'll just fill in the details. So it's c plus a times the cosine of b times t minus d. They said to use t here. So let's write our equation then. C, the sinusoidal axis we said was 5, plus a, the amplitude is 3, times the cosine of b, remember, is equal to, or really the absolute value of b is equal to 2 pi divided by my period. So it's 2 pi divided by 1.6 is the period that we have from up above. And that's times t minus the value of d, which d is your phase displacement, which is where that maximum occurs, is at 0.4. So there is our sinusoidal equation. And I would leave that, as far as the value of b is concerned, I'd leave that as 2 pi over 1.6. It's nice to write it in that form because if it's 2 pi divided by some number, that number you're dividing by is the period. So I'd leave it just in that form. Don't try to simplify it. All right, for part B now, it says to write an equation for the derivative, y prime. So now that we have y, we should be able to find the derivative of it. Y prime of t. So the function that we're looking at here is actually a sum of two functions. It's 5 plus 3 times that cosine. So we have, first of all, the derivative of a sum to deal with. So derivative of the first function, derivative of 5 is 0, plus derivative of the second function. Now the second function is 3 times cosine. That's actually a product, or excuse me, it's actually a constant times a function. It is technically a product of those two, but it's a constant times my function. So my rule is the constant stays out front times the derivative of my function. Now look carefully at the function you see there. That function is actually a composite function. You have cosine as the outside function, and all of this, which is actually a linear function, it's just 2 pi over 1.6. That's some constant times t, and then minus that constant at the end there. So that's a linear function, mx plus b. So use chain rule to find that derivative. So derivative of my outside function, derivative of cosine is a negative sign times, or not times, but I'm going to evaluate that at the inside function. Derivative of the outside is the first step of chain rule. Evaluate at the inside. 2 pi over 1.6 times t minus 0.4 is the inside function. And then we multiply it by the derivative of the inside, which if you look at the inside function, it's really a constant, 2 pi over 1.6 times some function. So just follow your rule for the derivative of a constant times a function there. The rule is the constant stays out front times the derivative of our function, which derivative of t is 1 minus the derivative of 0.4 is 0. Or in other words, you'll notice that the derivative of that inside turns out to be, because it's a linear function, just that coefficient in front of t. It'd be the 2 pi over 1.6. Let's just rewrite that here slightly. I'm going to go ahead and combine the 3 with the 2 pi over 1.6 there, so as well as the negative. I've got a negative 6 pi over 1.6 times the sine of 2 pi over 1.6 times t minus 0.4. There is our derivative. All right, let's see what it says for the next step of this. It says for part C, how fast is the mass moving for these values of t? Now again, y tells you the location of that mass. It tells you the distance it is from the ceiling. So the derivative is actually telling you the rate at which the distance is changing. It's telling you the speed or the velocity at which this thing is moving. So all I got to do is take my derivative function and plug in these values here. So they wanted to find the derivative at 1. We'll use our calculator, by the way, to do this. So I'm just going to write down what we're going to calculate, and then we'll punch it in our calculator. And they wanted me to evaluate it at 1.5, and then finally the derivative at 2.7. So let's see what we end up with. Let's take our calculator and we'll plug into y1 that derivative function we came up with. So we end up with negative 6 pi over 1.6 times the sine of 2 pi over 1.6 times t minus, or x minus for our case here, x minus, I forgot what that value was here, just a second, x minus the 0.4, 0.4. Okay, so there's our derivative function in y1. Let's go to our table. I'm just going to put this into ask mode so I can just type in the values that I want. So I've got 1, 1.5, and 2.7. And so here are the 3 values we end up with. So at 1, we end up with a negative 8.330. Negative 8.330. At 1.5, it turns out to be 10.884. 10.884. And finally at 2.7, it was a negative 4.508. Negative 4.508. Those are the values that we end up with. All right. Now we should also indicate units here for these values. So going back to what they used for units in measuring y they said was measured in feet from the ceiling, and our time, t, was measured in seconds. So all 3 of these are measured in feet per second. And again, if you go back to the other way that we can write the derivative, remember y prime of t is the same as saying it's the change in y, dy, over the change in t. And that really helps you see the units here, that y is measured in feet divided by, we're dividing that by, t is measured in seconds. So that really tells us the units there if I go back to that fractional form to represent my derivative. All right. Look at D. D says that t equals 2.7 seconds is the mass moving up or down, and justify your answer. Well, for part D then, I can see that at y at 2.7 from my previous work there was a negative 4.508. So because the derivative there is negative, that tells me my function must be decreasing. Okay? Since y prime at 2.7 is less than 0, then y is decreasing. Now it still doesn't tell me which direction the mass is going. That's the question. They didn't ask whether y is increasing or decreasing. They said, is the mass moving up or down? So you have to look at how they've measured y here. So I'm going to just kind of roughly sketch this picture that they gave you in the book there. You got this spring hanging from the ceiling attached to this mass here. And they said that we're measuring y as this distance right here, the distance from the ceiling. So if y is decreasing, that means y is getting smaller and smaller and smaller. So that means this distance y is getting smaller and smaller and smaller, which means the mass must be moving up. Okay? So the mass is moving up. Okay, and that's what they were wondering. Which direction is the mass going? Is it moving up or is it moving down? And that's the justification to our answer. You always have to go back and check to see how they've measured y to help you figure that out. Just because it's negative did not mean that it's moving up. In this case, we were measuring y from the distance from the ceiling to our mass. Realize that if we had measured that in a different way, I know they didn't measure it this way, but if we had measured from the floor, if we had said y was measured that way, now all of a sudden when y is negative, that means the mass would have to be moving down. Always go back and check how they measured that initial quantity y there. All right, finally, for part E. E says, what is the fastest the mass moves, and where is the mass when it is moving this fast? All right, so the fastest that it moves. So in other words, they're talking about the velocity, the rate at which the mass is moving, but I want to know when it's moving its fastest, when it's at its greatest, when it's at a maximum. Okay? So if I have some function here, we're just going to take kind of a little side note here. If I have some function that has a maximum, let's call this function f of x. This function has a maximum right here at this point. And the way that I can use calculus to help me find that maximum is to recognize that the slope at that point, if I sketch the tangent line, is 0. So at that point, f prime of x, its derivative, is equal to 0. So given some function, in this case f of x, to find the maximum of that function, you find where its derivative is 0. So in our problem, they're asking when is your, what is the fastest the mass moves? They're asking when you have the greatest velocity. When's the velocity at its maximum? So in order to find that, I have to find out when the velocity hits a maximum. When the derivative of velocity, that means, is at 0. All right, so we need to find when v prime, oops, I shouldn't call it v prime though, because we didn't use that name in our problem. We called it y prime here. That v of t is equal to, or velocity is equal to y prime. So we need to find out when the derivative of the velocity, that's the second derivative in this case, is equal to 0. First derivative is velocity. I need to find out when the derivative of velocity is 0. And that's the work that you need to write down. You could actually go through and find out this value algebraically, but I'd suggest that you use your calculator to help you do that. And so let's graph this and find out when the second derivative is 0. So in y1, we already have y1 as the derivative. Let's just simply calculate the numerical derivative of y1. And we want to find out when it's at its greatest here. So let's see here. I don't need to have the original function actually. I don't need the velocity necessarily to sketch with it. I guess I'll go ahead and leave it in there, but we can get rid of it. And let's graph this from like 0 to, I don't know, let's go out to 20 here. I'm not sure exactly how far we need to go out, but we'll go out to 20 and see what that gives us. And let's use our table to give us a list of values that our function is going to go through from 0 to 20. I'll set my table up to start out at 0. We'll change it by 2. We'll put it in auto mode, just so I can see a list of values that this thing's going to go through. So it looks like our original function starts at 11.7 and then goes to basically 0 there and then to negative 11.7. It looks like our second derivative here is taking on some more extreme values. That's what I want to actually track there. So let's go to our window, and it looks like if I go from something like negative, let's go negative 60 to 60. Seems like that will be a decent window of this. We'll see how decent it is. So there's our original function. Guess that's actually showing a lot more periods there than I really need here. I'm going to change that here. I don't need to see that many. I'm going to just stop that. I don't need to go all the way up to 20. Let's go from 0 to, looks like 0 to 5 would be a decent window of this thing. There we go. That's looking a lot better here. So that's the velocity function. We want to find out when we hit our maximum velocity. So our maximum velocity is when the derivative is 0, and you can see that as that derivative function right now is sketching. Anytime I hit a 0, you can see that your velocity function, the original one, must be hitting either a maximum or a minimum. All right, so the one that I'm going to focus on is the one that occurs somewhere between 1 and 2 there, it looks like. My velocity was at a maximum, and so I'll just calculate the, the 0. Again, this right here is the maximum I'm going after, that guy right there. And I can find that by finding where this derivative function is equal to 0. So we'll let it crunch that for us and see what we get. So it looks like that right at 1.6, we get a value of 0. So t equals 1.6. Now, based on what we know about our sinusoids and where they hit their maximums, we could have determined that without even using the calculator, but that's how we would do this for any other type of problem. So the question was, what is the fastest the mass moves, and where is the mass when it's moving this fast? So all we found so far was where, at what time it occurs. I need to actually find out what the maximum actually is there. So on my graph there, I'll just trace the original function, the velocity function, to 1.6, and we get 11.781. So y prime at 1.6 turns out to be 11.781. And again, the units for this are in feet per second. And as far as where this occurs at, in terms of the location of the mass, when we hit the maximum velocity, the mass is moving on its way down, and when it hits the very bottom of however far it's going to go, it hits a velocity of 0. On the way back up, when it gets as high as it's going to get, the velocity again hits 0. So it's halfway in between the maximum and the minimum points is where we're going to get these maximum velocities at. So it's halfway between the upper and lower bounds. Of y of t. That's where those are going to occur. Okay? All right, that is the end of the first half of this.